All right, so today I want to go over the worksheet that I gave you guys. I know that for a lot of you, this is the cause of some struggles. So hopefully, as I go over this, you can follow along, and that should clear anything up. So I'm going to start with number 4. I think 1 through 3 you guys can do on your own. They gave you the answers on the worksheet. That's old stuff. So starting with number 4, the instructions I have over here on the right side. Part A, Part B, Part C. So Part A is going to be to find inflection points. Part B is asking for the interval where the function is concave up, and then C where the interval is concave down. So seeing as those are all second derivative things, I can just start taking the derivative. So the derivative is going to be f prime of x, 12x squared, plus 42x plus 36, some power rule. And then we can just take the derivative again to obtain the second derivative, which is going to give us 24x plus 42. And if you like things to be clean, we can factor out a 24. No. See? Mental math, not strong. We can factor out a 2. 12x plus 21. I think I probably should have just left it. Oh well. So here we have the second derivative. That's step 1. Step 2 is going to be to set that derivative equal to 0. Next step is going to be to solve for x. So here you can divide both sides by 2. And I mean 0 divided by 2 is still just 0. So we're left with 0 equals 12x plus 21. Subtract 21 and divide. X equals negative 21 over 12. And let's go back and check just to make sure I didn't do anything dumb. 3 times 4 is 12. 2 times 21 is 42. And the 36 doesn't matter. 24x plus 42. Factor out of 2. 12. 21. All right. Cool. So this is the x coordinate of a potential inflection point. Remember, with the first derivative, critical points, they can be critical points without being maxes or mins, but with the second derivative, we don't have an equivalent for critical points. Okay, we would just say, oh, that's a place where the second derivative is 0. It doesn't have a name. And then if the second derivative changes from positive to negative, then it's an inflection point. So show you what I mean. We'll put negative 21 over 12 on the map here on the horizontal line test. And let's make a note for ourselves to make sure we know this is the second derivative test. And now we need to check a point to the left and a point to the right. To do that, we need to kind of know what this value is. Let's see, if it was negative 24 over 12, that would be 2. So this is somewhere between negative 1 and negative 2. And because I can use 0, that makes my life easy. And negative 2 makes my life pretty easy. Those are decent points to check. Come back to here. And so we plug in 0 to our second derivative. Okay, that helps us make sure we know where to plug things in. So our second derivative, we plug in a 0. So I'm going to plug it in here, which is the same as plugging it in on some of the lower lines. But those are the lines where I started doing math to solve. So I want to just make sure that when I do a complicated problem, I always come back to the second derivative and not some version of the second derivative that I've manipulated already. So if you plug in a 0, you get 21 times 2, that's positive. If you plug in a negative 2, you're going to get negative 24, which is going to be negative times a positive gives you negative. Okay, it gives you negative 3 times 2 is negative 6, which is negative. Good. So this is, in fact, the x location of an inflection point. And because all they asked you for was the x location, you do not, or the x coordinate, you do not need to plug it back into the original function to get the y coordinate. So your final answer should just be x equals negative 21 over 12, and you box it. Next. So the next one, number 5, your function is 2x to the power of 1/5 plus 3. That's the color I want. So again, let's take the derivative. So the first derivative, f prime of x, is going to be equal to 2 over 5. We're just bringing that 1/5 down. 2 times 1/5, if you need, that becomes 2 over 1 times 1 over 5, which is 2/5. So it'd be 2/5 x to the power of 1/5 minus, we're bringing the power down by 1. So that's 5 over 5 is equivalent to 1. And this should be 1 over 5, sorry. So 1 over 5 minus 5 over 5 gives you negative 4 over 5. And the 3 goes away, perfect. And now we need the second derivative, f double prime of x. We're going to bring that negative 4/5 down. That's going to be negative 8 over 25. Just multiply across, times x, and we have to subtract 1 again. So we're going to go another 5 over 5 to give us that. And now we set this equal to 0. 8 over 25, x to the power of negative 9 over 5. And this is only 0 when x is 0. So, done. Again, this is not necessarily an inflection point. We have to test it to make sure. Negative 1 and 1, I love those. 1 to the power of 9 over 5. So remember, a negative just means that you flip it to the bottom. So this is the same thing as negative 8 over 25 over x to the power of 9 over 5. Okay, and then we can make that much prettier. This would be negative 8 over 25x to the power of 9 over 5. So from there, we need to see, is x going to end up being positive or negative? So if you put in a positive 1, then it's obviously positive. And then negative 8 over 25 is going to give us a negative number. 1 to the power of anything is just 1. So 25 times 1 is 25. Negative 8 over 25 is negative. Who cares what it is? But now if we plug in a negative 1, what happens here? So let's review what we do with fractional exponents. So this just means it's negative 1 to the power of 9, and then you take the 5th root. Okay, so we could rewrite this as negative 1 to the power of 9, and then you take the 5th root of that. So if we just did it in steps, negative 1 to the power of 9 is still negative 1. And the 5th root of negative 1 is still negative 1. Okay? So negative 1, or negative 8 divided by negative 1 is just positive 8. If you have, so here we have the 5th root of negative 1. If you have an odd number here, then it's okay to have a negative number under the radical. If that's an even number, then you would end up with the i's or whatever. So odds, good, evens, bad for negatives under the radical. So here we can see obviously it switched from positive to negative. So that means the derivative change, the second derivative changed sign from positive to negative. So therefore, we do have an inflection point at x equals 0. Oh, and the intervals, I forgot the other part. So from negative infinity to -1, we have a concave up. That is just because it's positive. So just like the first derivative shows that the original function is increasing when it is positive, the second derivative shows that the original function is concave up when it is positive. And from, oh, this should be a 0. There we go, my bad. And then from 0 to infinity, we're going to be, what is that letter? We'll make it a D. We're going to be concave down. Why? That's because the second derivative is negative. So when the first derivative is negative, the original function is decreasing. When the second derivative is negative, the original function is concave down. Done. And I think I skipped parts B and C on this one. It's going to be the same or similar thing. From negative infinity to negative 21/12, we're concave up. And from negative 21/12 to infinity, we're concave down. Okay. Moving on. Numero 6. Is that seis in Spanish? I think so, but I don't know it off the top of my head. I have to go in order. Negative. And let's make sure we're using appropriate terminology. F of x, f prime of x, and f double prime of x, so that we know where we're at. F of, there's no prime there. F of x equals. Cool. So taking the derivative, we're going to get negative 4x cubed plus 12x squared minus 4. Take the derivative again. Negative 12x squared plus 24x. Now this one I can guarantee simplifies is going to be, let's pull out the negative 12x, and we're going to be left with x minus 2. Now we can set that equal to 0. 0 equals negative 12x, x minus 2. And therefore, x equals 0 or x equals 2. So for this one, we might end up with 2 inflection points. We're going to want to put 0 and 2 on here. We're going to make sure we know that this is the second derivative. And we're going to test negative 1, 1, and I like to use 10. You could use 3 or whatever. Plugging in a negative 1, we're going to get negative 1 times 12 is positive 12. And then negative 1 minus 2 is negative 3. So a positive times a negative is a negative. If you plug in a 1, you're going to get negative 12 times negative 1. A negative times a negative is a positive. And if you plug in 10, you're going to get a negative 120 times 10 minus 2 is positive. So negative times a positive is a negative. So both of these are inflection points. This is going to be concave down, concave up, concave down. I trust that you guys know how to write those intervals out, and x equals 0, x equals 2. So we're going to save some time. Next problem. All right, this should be a fun one. You guys know all of your derivative rules, right? So y prime is equal to derivative of the first times the second plus the first times the derivative of the second. Y double prime equals, so this is no longer product rule because it's just a 1. So the derivative of e to the x is just e to the x. And the derivative of x e to the x, we actually just did that. It's going to be e to the x plus x e to the x. Done. And let's make it pretty. Equals 2 e to the x plus x e to the x. Whoops. Plus x e to the x. And I mean, if we wanted, we could get crazy and factor out an e to the x and be 2 plus x. So let's set this equal to 0. Next step. E to the x will never be 0. Never, ever, 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 ever. So the only time that this is 0 is when 2 plus x is 0. And the only time that is 0 is when x is equal to -2. And now we can put that on our second horizontal line test. -2. Let's try -10 and 0. If you put in anything into this x here, e to the x is always, always, always positive. So you could put in -4,982,000,000 and you could put in 6. It doesn't matter. E to the x is always positive. So all we care about is this right there. If that's positive, our second derivative is positive. If that's negative, our second derivative is negative. So put in a -10, we get negative. Put in a 0, we get positive. Done and done. It changed, so this is an inflection point. This is concave down. This is concave up. Beautiful. Tangent inverse. Who remembers how to do that? I don't. I have to look it up. You guys, however, before your AP test, it is assumed that you know that. And so that is something that you guys might want to review before the AP test is your derivatives of all the trig functions, all the trig inverse functions, derivative of all the trig functions, all the inverse functions. I mean, I guess technically they could ask you about the hyperbolic functions. Those are the ones with the H on it. I would skip those. I doubt that they'll ask you something on those, but they could. Was there anything else? And then the cosecants, the secant, and the cotangent, the 1 over your regular trig functions. So tan inverse is going to be, oh, whoops, 1 over 1 plus x squared. Tan inverse is the easiest one. Sine inverse and cosine inverse, there's a square root at the bottom, and for one of them it's positive and the other one it's negative. I never remember, but there you go. So this is the derivative, so let's make sure we write this out right. F prime of x is equal to 1 over 1 plus x squared. So we don't do that. F double prime of x is equal, oh man, I don't want to have to take the derivative of that. So there are two ways you could take the derivative. One is the quotient rule. Low 1 plus x squared d high 0 minus high d low all over low squared below. The other way that you could do this is to just make this 1 plus x squared to the power of -1, and then use chain rule. That's what it's called. So if we did chain rule over here, that'd be -1 plus x squared to the power of -2 times 2x, which you see is going to come out to -2x over 1 plus x squared squared, which is exactly the same as what we have here once we simplify. So let's get rid of this because it's times 0. F double prime of x is going to give us -2x over 1 plus x squared squared. We can set that equal to 0 plus x squared squared. And then we go, dear, when is this 0? Well, it's 0 when the top is 0. And that's the only time that that's equal to 0. And then let's make a side note here. There is something that x cannot be. Because we have a denominator, let's just check this point. Oh, just kidding. So x squared can never be -1. So it turns out that we're actually good. So let me just go over that again. Sometimes you have something in your denominator that would mean that the denominator could equal 0. So for example, if we had -2x over 1 plus x, then we would have, okay, well, x cannot be -1. But because x is squared, that whole term will never equal -1, which means this whole thing will never equal 0. So we're good. We don't have to worry about it. So x equals 0 is our only potential inflection point. We need to confirm that it is an inflection point. Try -1, try 1. We're going to plug it back in. So if you plug in -1, our denominator becomes positive, our numerator becomes positive, and our denominator is also positive, so that's positive. If we plug in a +1, our numerator becomes negative, and our denominator is still positive, so that's negative. So yay, it is an inflection point. And I think starting on number 6, they didn't require you to do the intervals anymore. But if you wanted to, there it is. And next. So almost done. I got 2 more. Fx is equal to that. So again, take the derivative. F prime of x is equal. This is product rule. So this is going to be x derivative of the first 1/3 x to the -2/3 times the second x minus 4 plus the first times the derivative of the second. Second derivative is equal. Multiply the 2/3 down, that becomes -2/9x to the power of -5/3. So that's the derivative of the first times the second, x minus 4, plus the first, 1/3 x to the -2/3 times the derivative of the second, plus the derivative of this last thing over here is 1/2 x to the negative 1/2. Oh, that is a mistake. This should be a 3, which means this should be a 3. Okay. Done. And looking at this, I mean, you could, I guess, pull a 1/3 out or something, but there's not much that's going to simplify here. So we kind of just have to leave it. Set it equal to 0. Don't feel like writing it out. And now I'm looking at that and thinking, I'm not going to solve that. There's no way. So I pull out a calculator, and by that I mean I check the answer on the website. Oh, I closed it. Well, in that case, I don't know what it is because I don't have my calculator with me because I'm an idiot. In that case, plug it into your calculator, graph it. Your calculator will do that for you, and you'll get an answer. You'll probably get more than one answer. And then you put them on a test, on a horizontal line test. My mistake. If you really need me to do that one or to get you the final answer, or show you how to do it on a calculator, let me know, and I can do that for you at a later time. Next problem. Yay. So if this is f, then f prime is equal to 3x squared minus 4x plus 1. F double prime of x is equal to 6x minus 4. And I'm not going to do any more. I think we're good. Tomorrow, I'll go over the free response question at the bottom. That is a fun one. So parts A and B are just to find, or part A is to find all the maximums. B is the inflections. So that's all stuff that we've done so far. And then intervals, concave up, concave down. We've done all that too. But the fun part about this question is that they didn't give you a function. They just gave you a graph. So we have to be able to tell where those things are on a graph without having the function, which is much easier than actually doing it with the function. So that being the case, you guys have a good one.